Welcome, everyone. So today we're going to be continuing on to a key element of our module of this course on agent-based modeling for health insight. This module has focused on issues of uncertainty with models, and we've looked at uncertainty induced by stochastics, uncertainty induced by parameter values. And we've looked at how scenarios, baseline scenario and various alternative scenarios, often depicting a counterfactual, a situation that hasn't been observed before, but we're interested in understanding what its implications would be within our model. These counterfactuals are often termed what-if scenarios at a more informal level. Now, today's discussion is going to be weaving together some elements of the past discussions, and particularly when it comes to issues of stochastics, when it comes to issues of parameter uncertainty, both have strong implications for the primary topic we're going to begin discussing today, which is calibration of agent-based modeling. But before we do that, I have some little bit of cleanup work to do last time because of an inartfully give an example that I thought showed some features that associated with adaptive policies. But in fact, due to my carelessness, I didn't name the model a different name. And so there were two version 9s floating around with different features. And it didn't actually communicate what I had wanted it to in terms of adaptive policies that are dynamic, where what's being decided over time differs based on the state of the system. Examples of these policies include triggering policies, engaging in larviciding of mosquito larvae if mosquito counts and infectivity level with West Nile reach a certain level, or undertaking a mask mandate, instituting a mask mandate if cases of infection reach beyond a certain point within school, or putting in place a broader prohibition against staff sharing if cases in nursing homes reach too high a level. There's a lot of cases where our responses are keyed by the underlying situation. Outbreak response immunization campaigns were another example I gave. And I wanted to show you, I felt it was incumbent upon me to show you at least one example of that. So I posted one, and I'd like to, with your leave, go take a look at it. So I'm going to share my screen so I can point you to this same example. And I want to draw your attention in the course site to Model for Interactive Use in class. It's version 10 of the hierarchical infection transmission model. Okay, version 10, not 9. In general, you should use versioning control systems for your models to distinguish different versions of your model. When you make a change that affects the behavior of the model, make sure you give it a new version. The best way to do that is typically to use a version control system like Git, in older times Subversion or RCS or SCCS. But at the least, you should name them differently so that you don't mix them up. So you can always go back and find the earlier version. If you're seeing an odd bug in the current version, you could see how far it goes back. You can recover that version for reproducibility of results. And you can keep track of which versions were used to produce what results. This can be a key asset if you need to go back and figure out why you were seeing certain results or when a certain bug was introduced, etc. And I fell short. I had feet of clay when it came to this version. And I made a change and I named it also version 9, but there was another version 9 which didn't have the change, and I was a bad boy. I was a naughty boy. So I posted this version 10, and I'd like you to download it, and I'd like you to load it up in your AnyLogic. And I'm going to switch over to that model separately. And I'm actually looking at a different model here, so I'm going to close this one, and I'm going to open up instead that other one. Okay. So here we go, version 10. And what I want to, without spending too much time in this, I want to remind you this is a hierarchical model, a multi-scale model. Normally in an agent-based model, we have 2 scales. We have the overall environment, the overall global environment, and people. We have at least 2 scales, and sorry, particular agents. But in many models, we have more than 1 scale. Sorry, more than 2 scales. So we might have individuals in classrooms, in schools, in an overall environment composed of many schools. Or we might have people in homes where there might be roommates or families. They're in neighborhoods, and they're in a city, and maybe a city's in a region and in a province. So we might have many levels, and there's this natural nesting that goes on with agent-based models, where in some packages like AnyLogic, just as a person in the external world might be in a city, and the city is in a region, the model structure mirrors that. And when you run the model, that person is nested inside of a city, which is in a broader environment, many cities. And so it is with this model. So if we were to double click on Maine, we'll find that the overall situation, you could think of it as a province or a region of a province, has cities, includes cities. And within each city, if you double click on it, there's a population here. And this population is composed of, if you go here, it's a population of agents, and it's person agents. And each person is characterized here in this familiar SEIRS type of fashion. Okay, so this should be familiar, but what I wanted to draw your attention to, so far I haven't really indicated anything differently. People are knitted together in networks within a given city. If you go look at city and you were to scroll down, you'd find that there's distance-based networks within the city with a certain connection range. And then if you go look at Maine, you'll find that the cities themselves are also in a distance-based network with a maximum connection range of city connection distance. Okay, so it is. And last time I did talk about targeted interventions, and I noted that, as would be anticipated from these scenarios here, you have the option of having targeted interventions. For example, interventions where you ask if someone is eligible for an intervention, and if so, where you perform the intervention. And different scenarios will specify different criteria for eligibility, and will have different impacts on those people who are eligible. Say, in this case, setting their contact rate to be a lower contact rate than the default contact rate, say. And this is something where we could, for example, focus on hubs, individuals with lots of connections, and lower their contact rate relative to the default of 1.0. In this case, find them quicker too by lowering their contact duration of infectiousness. So that's what we emphasized last time with this model. But what I want to emphasize this time is a bit different. You'll notice that within city, on the basis of a city, the city decides whether or not to, should be called consider performing intervention, but they decide whether or not to perform an intervention every week. And the criteria for deciding whether or not the intervention undertaken has to do with the prevalence that's obtained within that city. And so if the prevalence within their city's population is above a certain threshold, which is a parameter in Maine, then we will undertake an intervention. We'll visually signal it, and we will then test eligibility people in our city and enact the intervention on them. So in this case, we would focus on the hubs in the city, and we would lower their contact rate and the duration of infectiousness. Here, we would say everyone in the city is subject to a lower contact rate. So maybe we ask them to work from home if possible and engage in social distancing. And we'll institute a contact tracing program to find them quicker, to allow faster identification. The point is, this is being undertaken dynamically based on a dynamic condition here. It's not that we're saying ahead of time, intervene at the model at the start and see what the consequences are. It's not that we have a fixed time of the intervention. It's not that we say, 3 months after the model start, institute this change to lower people's contact rates. All those are possible, of course, but what this shows is something a little bit more subtle than that. And in fact, a lot more powerful than that. What we're looking at here is an adaptive decision rule, one which will choose different courses of action based on the underlying situation. And there's a huge space of possible such rule. Among other things, we could have different prevalence thresholds at the least, by which we might say, okay, it's worth undertaking this intervention. And we could have different scenarios which explore different thresholds. A lot of words here, but let's enact it. Let's operationalize it. Because remember, models are learning tools. And we learn from them by, in one of the biggest ways we learn from them is by running them. Models are not merely models that make our assumptions explicit and lay them out for others so that we can collectively critique them and advance them. Important though that is, they're operationalizable. They're operationalized by laying them out in this sufficiently precise way, in this case involving a bit of code, in other cases involving these state charts, etc. By laying that out in a sufficiently precise way, we can see its dynamic implications. We can see the behaviors induced by this model over time. And we could see the consequences of that rule and compare it to the consequences of other rules, maybe with different prevalence thresholds. So let's go look at this if we could. What I'm going to do here is I'm going to institute. So we'll have one where we just lower everyone's contact rate. There's another one, it says lowered contact rate, 10% prevalence threshold, but there's a problem with this. This should say default contact rate 1.0, so that we're just using the default. Notice when I change it to 1.0, it changed it back from being bold. Before this was 0.9, and it flags it as different than the default in the model. So I'm changing it to 1.0 here. And it's only when there's a 10% threshold of prevalence of infection in a given city. Under that case, we will intervene upon people in the city. Everyone in the city will be eligible, and we'll set their contact rate to 0.9. So we'll wait and see. We won't institute any interventions until there's a 10% prevalence in our city, and then we'll take action, is the idea. And we'll here instantaneously lower everyone's contact rate in that city to 0.9. Okay, so let's go. Maybe we'll look at the baseline first, because we need a reference. So I'm going to run the baseline here. And when we run the baseline, we'll see the basic setup of this model. And we should have 5 cities here. So where are, okay, that's curious. Where are these 5 cities? I suspect they're on top of each other. Okay, that's pretty odd. Did I change something here? Give me a second here, because I've run this model many times before, and I've not seen this. Was it something? Nope. Okay, so there it is. Okay, hey, let's go figure what's going on here. This is pretty curious. So I'm going to, my first guess is in Maine, so I developed a hypothesis. I suspect that the cities are not being distributed around, but I see the layout as random here. So I would expect that the cities are spread around randomly. Okay, I see there's 5 cities. I had another hypothesis, maybe there's only 1 city, but there are 5, and that jives with what I saw. Okay, so why are those cities not being drawn around? Okay, first of all, I'm going to see if it's something, I have another hypothesis. Maybe it has something to do with this particular scenario. So I'm going to run this count cities equals 10, just to see, is it something having to do with that scenario? If so, I'm not going to worry as much. And okay, it's out of memory, blah, blah, blah. But no, the cities are still atop each other. Well, I'll be, okay. This is getting more and more interesting, because I've run this model before and not observed this. First of all, I'm gonna raise my memory. I don't think this is memory related, but I just saw a memory thing. So I'm examining different hypotheses. These are really easy to rule out by making a change. Nope, the cities are still atop each other. There's 5 of them. Look at that. And if we were to go over here, we could see there's 5 cities and go between them. Maurice has raised his hand. Yes, Maurice.
Just to say, it seems to be working okay in the version I just downloaded. Wondering.
Well, that's good news. It's not as good news for me demoing it, so I'm going to try to figure this out. Okay. It's really great that you folks are doing that. Maybe I should download it, but I'm tempted to try to make this converge.
Oh, sorry, I hope it's I think in the main environment.
Sorry?
In the main.
Yeah, in Maine. Yeah. Yeah.
The city.
Yeah, there's cities there. Yeah.
Yes.
Oh, you're saying the check mark. Okay, yeah, maybe it's because I'm not, I didn't check that. Yeah, that's possible. Normally that would always be checked. Good call, Benjamin. Okay. Benjamin is the, was that Benjamin?
Yes.
Okay, awesome. Okay, that's great. Maybe I unticked it by accident. Benjamin wins the gold. Okay, that's great. Okay, so we should call this version Benjamin. Okay, so here we have 5 cities. We are running the baseline with the Benjamin fixed version. And we start out an individual infected and it's spreading here. And if we speed it up, the infection is going to spread. Some of these people may migrate. For example, some of these folks who are yellow might be the early stage. Notice that city is turned red all around it. That's an indication that it's in, lockdown mode, or it's instituted a public health order to lower people's the contact rate. But people are diffusing over to other locations. So far, it looks like they're mostly recovered individuals. We can continue to run it, but the point is, I did want to show how these cities go successively into lockdown as the infection levels reach beyond that beyond the threshold. And here the prevalence threshold to intervene is 1%, but nobody is eligible for infection, and there's nothing we do if we were to intervene. So it's a 1% threshold. To say it's a lockdown is incorrect. They just declare an emergency, but there's no change made. By contrast, this lowered contact rate 10% prevalence, I again emphasize that the default contact rate should be 1 here. We again have 5 cities, but we do in fact intervene. When it reaches 10%, we intervene upon everyone and set their contact rate to 0.9. So here we'll have an alternative scenario where we have the same number of cities, but there's a rule in place which will attempt to lower contact rates if we reach 10% prevalence, which is, I might note, very, very high prevalence. And you'll notice the cat's already out of the bag. So here's an exposed person, here's another exposed person in 2 different cities, it would appear. And so we've got already infections seeded here in several cities. Maurice, did you have a further question? Or is that a legacy hand?
I think it's a legacy hand. Thought
Okay.
I'd lowered it.
Okay, thanks. Okay, so here we have 2 incipient outbreaks, but no lockdowns have been instituted yet. We don't see, now they did, but already it was up here in this third city. And you can see people are migrating to other cities, and perhaps amongst them will be an infected person eventually that might cause these cities to outbreak. So naturally, we could go and undertake interventions with different thresholds, maybe a more early acting threshold of 1%. You could copy this scenario and paste it in at the top and just change it to be 0.1 and make it lowered contact rate 1%, for example. And we could experiment with that. I'm not going to take the extra time to do it, but I think you get the gist of this, that by doing this, we could basically enact different decision strategies or explore, investigate the impact of different strategies for intervening dynamically over the course of of responding to an outbreak. We can put in place agent rules associated with agent perception. Here, the agents are cities, and the rule is if the prevalence is above a certain level, take this action. And we could experiment with different actions, different thresholds, different criteria for judging, etc. And sort of weigh the trade-offs between these, compare them to a static strategy, which would simply, lower the contact rate up front, or, engage in faster contact tracing alone, or something along those lines. So here we're examining an honest to goodness adaptive strategy, an honest to goodness dynamic strategy that is undertaking different actions based on the observed situation in the world. And if by chance, because of stochastics, the infection doesn't take off, this rule may never be enacted. If by contrast, it goes to other cities and not this city, this rule will never have to be enacted. But if it comes to this city early, we're ready for it with this rule. That's the idea behind adaptive dynamic rules. And agents, the sort of the notion and the construct of an agent within agent-based modeling provides a really natural way to have these actors that declare an emergency, for example, in a city, or it could be in a household, right? It could be household decision-making about how to handle illness on the part of one of the kids in the household. Do you send that kid to school or not, for example, or do you keep them home? Does that mean the parents can't go to work, etc.? These are things we can enable in an agent model and look at the impacts of different measures for judging action, different types of decision rules, and different types of actions to be undertaken. And generally, although I glossed over it, generally for each of those interventions and the baseline, of course, we would judge it against a certain outcome. We'd be evaluating measures of, how good or how bad a job we did, how many cumulative deaths there were, how many infections there were, or how many individuals were admitted to hospital or needed ICU care, or what was the peak hospitalization census, hospital census or ICU census, etc. So that's just a little bit about dynamic rules, dynamic intervention. And because agent-based modeling is articulated at a level of individuals who have perceptions, who have a certain amount of autonomy to enact rules, and because it's often includes multiple levels, it has a very nice feel to it for enacting decision-making on the part of schools, long-term care facilities, acute care facilities, individuals, families, cities, provinces. You can describe these things with agent-based models. Okay, so that's what I want to finish up from last time as kind of a legacy matter. But I want to now turn to a topic which will draw on some of those ideas, in particular this idea of the calibrated baseline. So I'm going to stop my sharing, and I'm going to